Welcome back to the Deep Dive. Ready for another one? Today we're taking a deep dive into the world of electromagnetic induction and alternating currents.
Oh, yeah,
They're pretty big.
those are fascinating topics.
Yeah, intimidating for some people, right?
For sure.
But don't worry, we're going to break it down and make it fun.
Absolutely.
Whether you're prepping for a meeting or, just trying to refresh your memory from some physics textbook,
Right.
we're going to make this understandable and hopefully fun.
Right. And these concepts are really fundamental to so much of the tech that we use every day.
Yeah.
So understanding them is super practical.
So let's start with the basics.
Okay.
Magnetic flux. Have you ever, thought about like a loop of wire,
Yeah.
like a lasso or something, and you've got these magnetic field lines passing through that loop.
Yeah.
The amount of those lines going through the loop, that's essentially your magnetic flux.
That's a good way to visualize it. It's not just the strength of the magnetic field, though. It's also the area of that loop and the angle, you
Right,
know,
yeah.
like how it's sitting relative to the field lines.
So if I was to tilt my lasso, I'm essentially changing the amount of magnetic flux passing through it.
Exactly. And that's where things get really cool.
Okay.
Because when you change that magnetic flux through a loop, you induce an electromotive force, or what we call EMF. It's like you're creating a little tiny electric pressure just by moving a wire around in a magnetic field.
Whoa, wait. So you're telling me just by moving a wire, I can create electricity?
Yeah,
That's wild.
that's basically how a generator works.
Really?
Yeah, they use motion.
Mechanical motion.
Exactly, to create a changing magnetic flux, and then that induces an electrical current.
So like those giant turbines in a power plant.
Exactly. Those things are connected to huge coils of wire that spin within a magnetic field. And so that spinning creates that constant change in the magnetic flux, which induces the current that powers our homes.
Wow, that's crazy. So, okay, so we've got a changing magnetic field inducing this EMF.
Right.
But what about this motional EMF thing? Is that the same thing?
Yeah, it's closely related.
Yeah.
It's the EMF generated when a conductor moves through a magnetic field.
Okay.
So picture like a metal rod just slicing through those magnetic field lines. And that motion itself induces an EMF across the rod.
So it's like the movement is creating the electric pressure even without like a loop of wire.
Exactly. And the faster the rod moves, or the stronger the magnetic field, the stronger that EMF is.
Interesting.
But here's the thing. The direction of that EMF actually depends on the direction of the field and the direction the rod's moving.
So it's not just about moving the wire or the rod. It's about how they're moving in relation to that field.
You got it. It's all about those angles and directions.
Gotcha. This is making my brain hurt a little bit. It's a lot.
It's a lot to visualize, for sure.
Yeah. So this brings us to self-induction, right?
Right.
What is that?
So self-induction, the changing magnetic field, is actually made by the coil itself.
What?
Yeah. So imagine you have a coil and you're running a current through it.
Okay.
That current generates its own little magnetic field around the coil. And if that current changes, the magnetic field changes too.
Okay.
So it's like the coil is reacting to its own magnetic field.
So it's like the coil is creating the field and then reacting to it at the same time.
Exactly.
Yeah.
And that changing magnetic field induces an EMF in the coil itself, and it opposes the change in current.
Oh, wow.
So it's like it's resisting any fluctuations in the current.
It's trying to like stabilize itself.
Yeah, you could think of it that way, and that's actually super important for a lot of electrical circuits.
Oh, so it's not just like a cool phenomenon. It's actually practically useful.
Oh, yeah, absolutely.
Okay, I'm starting to see how all of these pieces fit together. So
Yeah.
we've got these changing magnetic fields,
Right.
inducing EMS, whether it's from an external magnet or from the coil itself. And this is all happening because of like this fundamental relationship between electricity and magnetism.
Absolutely. They're really two sides of the same coin.
My mind is blown.
Yeah, it's pretty wild.
Okay. So,
Yeah.
so where do we go from here?
Well, now that we kind of have these basics down, I think we can start looking at how they're used in AC circuits.
Okay.
You know, thinking about transformers and inductors, capacitors.
Yeah.
All of these rely on the stuff we've just been talking about.
This is where it gets really practical, right?
Totally. Get ready to see how this stuff is used in everyday life.
All right, I am ready. Let's get into it. All right, so we talked about magnetic flux and electromagnetic induction and self-induction, all that good stuff.
Yeah.
Now let's get into AC circuits. But before we get into that, I'm curious.
Okay.
We were talking about changing magnetic fields create these currents, right? Wouldn't that, like, result in a super chaotic current? Like constantly changing direction?
Yeah.
How is that useful?
That's a great question. That induced current does change direction all the time in response to the changing magnetic field.
Right.
And that is alternating current, or AC. It goes back and forth,
Yeah.
like a wave.
So instead of fighting that, we just like embraced it.
Pretty much.
That's so cool.
Yeah, and there's a few good reasons why AC became the main way we do power.
Yeah.
For one, it's easier to make.
Yeah.
And send over long distances.
Right.
Remember those giant turbines?
Yeah.
They naturally create AC.
Right as they're spinning.
Exactly.
Okay. And we can use transformers to like step up the voltage or step it down.
Right.
Which is super important for sending power efficiently.
Exactly. That brings us to one of the key parts of AC circuits, the inductor.
Oh, yeah. Inductors.
You talked about self-induction?
Mm-hmm.
That's what inductors are all about.
Okay.
But in AC circuits, they do even more.
So remind me, how do they behave in an AC circuit? Don't they like resist changes?
Yeah, they do. But remember, the current in AC is constantly changing direction.
Oh, right.
So the inductor is always fighting that change. And that creates a kind of resistance to the flow of AC.
Okay.
We call that inductive reactance.
So it's like it's trying to slow down the AC current,
Mm-hmm.
but it's a different kind of resistance than like a regular resistor.
You got it. With the resistor, the resistance is the same no matter the frequency.
Okay.
But with an inductor, the resistance goes up as the frequency increases.
Oh, so it's like it's more resistant to high frequency stuff.
Exactly. And that makes them really useful for filtering out frequency.
Oh, like getting rid of the unwanted stuff.
Yeah, exactly.
Okay, that makes sense.
Yeah,
So inductors are like the bouncers of the AC circuit.
I like that analogy.
Right. What about capacitors? Where do they fit in?
Capacitors are like the energy storage.
Oh.
They store up charge and then release it later.
Okay.
In AC circuits, they kind of do the opposite of inductors.
Opposite how?
Inductors fight changes in current.
Mm-hmm.
Capacitors fight changes in voltage.
Oh.
So as that AC voltage goes up and down,
yeah.
the capacitor tries to smooth it out
Oh.
by absorbing or releasing charge.
So it's like the capacitor is trying to keep the voltage steady while the inductor is trying to keep the current steady.
Exactly. And just like inductors have inductive reactance,
Right.
capacitors have capacitive reactance.
Okay.
But here's the interesting thing. Capacitive reactance goes down as the frequency goes up.
Wait, so it's the opposite of the inductor.
Yep.
So higher frequency means less resistance for a capacitor.
You got it. So an inductor might block those high frequencies,
Mm-hmm.
but a capacitor will let them pass through.
So if you combine them,
Mm-hmm.
you can get some pretty cool filtering going on.
Exactly. You
Yeah.
can shape that AC current to do what you want.
Oh, wow.
And when we put these components together,
Okay.
resistors, inductors, capacitors,
Uh-huh.
we get what's called RLC circuits.
Oh, yeah. RLC circuits.
And these circuits can do some really cool stuff,
Okay.
especially when you think about resonance.
Resonance. I remember you mentioned that earlier.
Yeah.
It's like pushing a swing at the right time to make it go higher.
Exactly.
How does that apply to circuits, though?
Well, in an RLC circuit, resonance happens when the inductive reactance and the capacitive reactance cancel each other out.
Cancel each other out. How is that possible?
Remember how inductive reactance goes up with frequency,
Yeah,
but capacitive reactance goes down?
right.
Well, at a certain frequency, those two reactances are equal,
Oh,
but opposite.
okay.
So they cancel out.
So it's like they're balancing each other out.
Yeah. And at that point, something cool happens.
What happened?
The circuit becomes super responsive to that frequency.
Okay.
Like it's tuned to it,
Uh-huh.
so that frequency passes through easily,
Okay.
but other frequencies are blocked.
It's like a super selective filter then.
Exactly.
Yeah.
And this is used in a ton of applications.
Really?
Yeah, like radio tuners, even MRI machines.
Wow.
It's a fundamental concept that lets us really use the power of AC circuits.
Okay. This is getting pretty complex.
It is?
But I'm starting to see how it all fits together.
Yeah.
It's like we're building a puzzle.
That's a great way to think about it.
And the more pieces we add, the more we see how complex it all is.
Exactly. And there's still more to explore.
Okay. I am ready for the next piece of the puzzle.
All right, let's do it.
Okay, so we've talked about how inductors and capacitors work in AC circuits,
Right.
and even how they can like team up to create that resonance thing.
Mm-hmm.
It's crazy that these like simple components can do all that.
Yeah. It's amazing how much complexity you can get
Yeah.
from just a few basic building blocks.
Yeah, but before we get into even more components and stuff,
Okay.
there's one more big concept we got to talk about.
What's that?
Power
Oh, yeah.
in AC circuits.
Right.
Now, isn't that just like, how much electricity is flowing?
Well, in DC circuits, it's pretty simple.
Okay.
It's just voltage times current.
Right.
But AC is always changing, remember?
Yeah.
So it gets a little trickier.
Oh, I can imagine.
Ugh.
So how do you even measure power if it's always going up and down?
You have to think about two things.
Okay.
The power at any given moment,
Okay.
we call that instantaneous power.
Okay.
And then the average power over a whole cycle of that AC wave.
So it's like instantaneous is like a snapshot.
Yeah, like a quick peek.
Average is like the big picture.
Exactly. And usually we care about the average because that tells us how much work the circuit can actually do.
Makes sense.
Yeah.
But isn't average power still just voltage times current?
It would be if they were always in sync.
Okay.
But remember those phase shifts?
Oh, yeah, with the inductors and capacitors making the current lag or lead.
Right. And when they're out of sync,
Yeah.
the average power is actually less than just multiplying the voltage and current.
Huh, interesting. Okay, I'm going to stop you for a second. What is RMS, voltage and current?
Oh, good question. RMS stands for root mean square.
Okay.
It's basically a way to describe the effective value of an AC signal.
Okay.
Kind of like an average, but it takes into account the fact that AC is always changing.
So instead of using the peak values, which are just for a moment,
Right.
we use RMS to get a better picture.
Exactly. And that's where power factor comes in.
Oh, yeah, power factor. You mentioned that before, right?
I did. It basically tells you how well the circuit is using the power it's getting.
So a high power factor means it's using it well.
Yep. Low power factor means some energy is wasted.
Oh, that's not good. And that's because of that phase difference?
Exactly. The closer they are in sync, the higher the power factor.
Okay.
And the more efficient the circuit.
So if a circuit has a low power factor, we're losing energy somewhere.
Yeah, and in big factories and stuff where they have tons of machines,
Uh-huh.
low power factor can be a huge problem.
Really?
Yeah, big energy bills, and it can even stress the power grid.
Oh, wow. So what can you even do about that?
You can do something called power factor correction.
Okay.
Usually you add capacitors to the circuit.
Wait, capacitors?
Yeah.
But those make the current lead the voltage, right?
They do, but the problem is inductive loads make the current lag.
Oh, right.
The capacitors balance it out.
Ah, so it's like a balancing act to get that power factor up.
Exactly. And that saves energy, saves money, and makes everything run smoother.
That's awesome. So we've gone from like basic magnets and wires
Yeah.
to like optimizing power in these crazy circuits.
It's pretty cool.
It is. I'm kind of amazed by how it all connects.
Yeah, and we've really just scratched the surface.
Oh, man.
There's so much more to learn about AC circuits.
No, I feel like my brain is full for today.
I hear ya. It's a lot to take in.
Yeah, but this deep dive was electrifying.
I'm glad you enjoyed it.
Yeah, thanks for walking me through all of that.
Of course, anytime.
All right, everyone, thanks for tuning in to the deep dive.
See you next time.
We'll catch you in the next episode.